everyone, this is Varun. Welcome to Aerospace Structures. Today we are going to discuss about the reciprocal theorem. Okay, what this reciprocal theorem says, let us go. Here we have taken an linear elastic member or a body. Here the linear elastic signifies that when we plot epsilon and sigma, you are all aware that there is an elastic curve and there is a yield and something like this. We are at this elastic point. The Hooke's law holds good. That is sigma is equal to E epsilon. And all the theories which we are going to study and which we have studies based on the linear elastic theory. That is, Hooke's law holds good. And moreover, it follows the principle of superposition. And let us understand what the principle of superposition. For example, when you take a cantilever beam and when you apply a load of magnitude P1 and you find a deflection of delta 1. When you replace this load with magnitude P2, then you find the deflection delta 2. And finally, now what you do is that you apply the extra load of previous one P1. And what you observe is that the deflection will be delta 1 plus delta 2. This is the principle of superposition. And the principle enables us to express the deflection of any point in a structure in terms of constant cohesion and applied load. When there is a arbitrary section, when you apply a load on it, that is say load of P, and the load P can be expressed as some P times some constant times, let us say the constant has A times the deflection. The deflection can be represented as delta times some magnitude A into P. A is some arbitrary constant. It depends upon the material. Okay, let us look into it. For example, a load P1 is applied at a point 1 in linearly elastic body will produce a deflection delta 1 at a point is given by OK. Let us look into this. This is a schematic of an arbitrary solid body in which it is restricted at 2 points, that is say at this point and at this point, and we have applied an n number of points at n number of loads at n number of points. When I apply a load say P, it has produced a deflection of delta at some point delta, and the deflection corresponding to this load can be expressed as delta is equal to some constant A into times P. That is the scenario here. When a load P1 is applied, for example, let us take some load P1. When we apply a load P1 in a it will produce a deflection of delta 1 at a given point. That is, it produces a deflection delta 1 at this point, and it is given by delta 1 A11 into P1. Okay, now instead of one load, we are going to apply the n number of loads at n number of points. Say P1 to n be the n number of loads which is acting on linear elastic member. Then the influence coefficient or flexibility coefficient A11. That is, we are going to define the new term called as the influence coefficient or the flexibility coefficient. Deflection at a point 1 in the direction of P1 produced by a unit load at a point 1 applied in the direction of P1. That is, deflection at a point 1. When you take a deflection at a point 1 in the direction of P1, that is in the same direction of P1, say it is of delta 1. produces a unit produced by a unit load displacement, and P1 can be considered as a unit load of 1 applied in the direction of P1. This is the influence coefficient. And here the most important thing is that the direction of deflection is one of the most important thing. When you are considering a influence coefficient, the direction of displacement and the direction of load plays a very important uh, role in defining the influence coefficients. And clearly, if the body supports a system of loads such as those shown in figure, and if we apply a n number of loads, which is a practical scenario of any of the solid body, say we are applying a load P1 to n, will contribute the deflection at a point 1. And moreover, the deflection at a point 1 is not only because of load P1. It is also because of load P2, P3 and so on Pn. That is the number of loads which is applied. Thus, the corresponding deflection delta 1 at a point 1 is given as follows. That is, when you consider a deflection at a point 1, the deflection is due to P1 as well as the deflection is due to P2 and so on. And moreover, the principle of superposition also holds good. When we observe these two, mathematically we can write the statement as the deflection delta 1 at a point 1 is given as A11 P1 plus A12 P2 so on A1N Pn, where A12 is the deflection of point 1 in the direction of P1 produced by a unit load at a point 2 in the direction of P2. Okay, when you A12 is the deflection produced by the load P2, that is where it is, this is P2. This is the deflection produced by the load P2 in the direction of P1, and the P2 will be a unit load. This is the influence coefficient of deflection 1 and the P2. And finally, when we consider n number of loads, which can be expressed as following matrices. Now I read as delta 1 is equal to A11 P1 plus A12 P2 so on A1N Pn. And similarly, when we take the case of 2, the deflection 2, when you observe this, and here the deflection 2, we have an influence coefficient of A22 and A21 and so on. Okay, going with this ahead, and finally in matrix form, what we can write is delta is equal to A into P. Sorry, here what we have done is that we have segregated these loads and the deflections, and we have find out the relation between the loads and relation, which can be written as delta in matrix form equal to some matrix A into P. Here when you observe this, delta is 1 cross n matrix and A is n cross n matrix and P is 1 cross n matrix. That is, if we know the loads and if we know the influence coefficients, we can know the deflection. Or in the vice versa, if we know the deflections and know the influence coefficient, we can identify the loads. Okay, the third term on the right hand side of equation results from the additional work done by P1 as in the displacement through the further distance A1 to P2 by the action of P2. Okay, when we apply a load in the direction of P2, there is some work done along the direction of P1, and that work is done because of load P2. If we now remove the load and apply P2 followed by P1, we have the following equation. Now what we are doing is that we are expressing the strain energy at a point. The strain energy at a point 2 can be written as P2 by 2 times A22 P2 plus P1 by 2 A11 P1 plus P2 by 2 A21 P1. And by the principle of superposition, which we have discussed in previous class, what we can write is, by the principle of superposition, the strain energy stored is independent of the order in which the loads are applied. Hence, U1 is equal to U2 and A12 is equal to A22. What does it say is that the strain energy doesn't follow the order of loading. It only follows the principle of conservation. For example, when you take a rod, when you apply a load P1, it has an extension of delta 1, and let us say it has a strain energy of U1. When you increase the load by P2, it has an extension of extra delta. For instead of P2, let us say delta P. It has an extension of delta something. And finally, the strain energy has been increased from U1 to delta U1. But when you change the order of loading, that is, instead of applying P1 first, you apply delta P1 load and you find the deflection of delta 1, say. And when you increase the load by P, and the extension will be by delta, let us say this delta. And finally, the strain energy can be written as delta U plus U. That is, the strain energy doesn't changes in the order of loading. It doesn't matter at all. It only obeys the principle of conservation of energy. And finally, from this equation, what we can conclude is that one thing, U1 equal to U2 and A12 equal to A21. And thus, in the simplest form, what we can state is that the deflection at a point 1, that is, when you consider any point 1 in a given direction due to unit load at a point 2, let us draw an arbitrary body and note it as point 1. This is point 1. I will be clearly drawing this. Let us take some arbitrary body and we have constants on this arbitrary body. Now what we are going to do is that we are locating the 2 points 1 and point 2. That is, the deflection at a point 1 can represent as delta 1 and the deflection at a point 2 is represented as delta 2 and the load at a point 2 is P2 and the load at a point 1 is P1. And this is a schematic and rough diagram of a linear elastic member with 2 loads. Deflection at a point 1, okay, that is delta 1 in the direction of unit load at point 2, okay, this is applied in the direction of P2. In the second direction is equal to the deflection at a point 2 in the second direction due to unit load at a point 1 in the first direction. This is what it is saying that. And similarly, in a similar manner, we derive the relation between the moments and rotations. Thus, the rotation at a point 1 due to unit movement at a point 2 is equal to the rotation at a point 2 produced by a unit movement at a point 1. And finally, these are the 3 statements in which it is followed by the Maxwell Reciprocal Theorem. That is, one, it is defined for the deflection, and other it is defined for the moments, and other it is defined for the rotation. Either the case, deflection, rotation or moments, the principle of reciprocal theorem holds good. And the most important thing what you need to observe is that the direction of load and the direction of the displacement. When you have a clear idea of these two, then you can easily find out the influence coefficients. Or if you have an influence coefficient matrix, then we can find either load is known, deflection, or if deflection is known, we can identify the load. And thank you very much. This is Varun Muruganti signing off.
Like, share and subscribe. Hit the bell icon for more updates.